In the last session, we saw two graph traversal techniques, namely BFS, that is breadth first search, and DFS, which is depth first search. We also mentioned that these techniques are useful in solving a lot of real life applications. In this session, we will look at some applications where these graph traversal techniques are used to solve the problems. Let us look at the problem where we have a set of tasks which have to be performed, and some of the tasks cannot be done until some other task is finished. So, there is an order in which the tasks have to be performed, and this is a situation which occurs quite regularly in our regular life. For example, let us consider a problem of taking a course, and we know a particular course can have a prerequisite course. Either a course can be done independently of all other courses, or there can be a prerequisite course. The problem is there a systematic way of linearly arranging the courses in the order they should be taken? Now, the prerequisite relationship of courses can be represented by a directed graph. So, if you look at this graph G, it represents the prerequisite structure or prerequisite relationships for the graphs, for the courses. In this graph, your nodes represent the courses and the directed arrows represent the prerequisites or the relationships between these two courses. So, the courses which are at this level have no incoming arrows, that means they have no prerequisites. So, can be done independently, whereas a course which is here has two prerequisite courses, and these two courses again have prerequisite courses. So, this course which is at the end of the graph has a lot of prerequisite courses to be done before this course can be taken up. So, we want to look at a systematic way of linearly arranging, so that the prerequisites structure is very clearly understood. So, topological sorting is a method of arranging this in the linear manner. It represents the graph as a directed acyclic graph. That means, there are no cycles in the graph and it is a directed graph, such that no vertex appear in sequence before its predecessor. So, if I look at the previous case, it can be rearranged linearly like this. That means, now if you look at course which is here ICS whatever 353, which is at this particular position in linear order, we see that for doing this we need to do course 202, 201 and 102. So, we can see this here, that for doing this course, first one has to do 202, then 201 and 102. So, this particular thing is represented in this arrow. Similarly, if you look at this, one also has to do 102, 253 to do 353. So, you do 102 and then you have a arrow here, and from here you have an arrow which is here. So, the graph A we see can be topologically sorted as shown in graph B. So, we are going to look at a systematic way of doing this. That is, the input will be this graph, this is the input to our procedure, and this graph will be the output. So, the procedure that we look at is going to take a graph which is directed and output a directed acyclic graph with the property of topological sorting. It is easy to see that topological sorting is not unique. That is, there could be many ways in which a graph can be topologically sorted. Let us look at this example. G is a directed graph, whereas on the right hand side we have different topological sortings of the same graph. As we see here, if I look at the structure A, B, and then I can write C, because or you could have started, as we see that B prerequisite A and C is prerequisite is also A. So, after A one could have either B or C. Topological sorting of a graph is not unique. In fact, here we have written down 4 different ways of topological sorting the graph. You could have more ways. So, when we are written here, this actually is A, B, C, and one will have to write down all the relationship between them. So, actual graph will be, you will draw A. So, if I look at the first sorting, so it will start with A, then okay, B, after B you have D, before that you will have A to C, then you can have B to D and things like that. So, you can have B to D, then you have E, you can reach it via B or via A. So, you will have and so forth E, then you can draw F and G H I. So, one can do then F will come here and you have F is here. So, you have C to F. So, C to F is there, that is all. So, one can actually represent for the set S1 the corresponding directed acyclic graph which is linearly arranged. So, this can be just completed to get the topological sorting of the graph. So, the algorithm that we propose would give us one way of doing a topological sort on a graph. We had already seen depth first search algorithm. We add a certain property to DFS which will help us in the topological sorting of a graph. So, to the standard DFS algorithm that we have already seen, we add a factor called time stamping, which is going to help us to understand how what are the prerequisites or what are the relationships or which is the vertex which is going to be visited first and then later. So, time stamping will allow us to rearrange our directed graph as a directed acyclic graph with precedence relationship. So, to do that we first initialize all vertices and color them white and timestamp them 0. So, as initialization all the vertices in the graph are colored white. So, you add one more field to your node and make that field as a white field. You add another field which is called a timestamp and initially all vertices are timestamped to 0. So, once you initialize this, you start visiting nodes or start traversing the graph in a depth first manner. Only as you go to the DFS traversal, we update the timestamps at each vertex and also update whether the vertex has incident edges which has not been traversed. So, as we go through the DFS traversal, we maintain two things, that is, one is the time and the other is whether the adjacency list at a particular node is exhausted or not. So, we start depth first search for a node which is white. So, initially we could start with any vertex as our start point for the DFS. So, as you start visiting, the first time you visit a vertex, you stamp it gray and time it as and update the time or increment the time. Now, for each node in the adjacency list of this vertex, if there is a node which has not been visited earlier, that means is white, we will continue our depth first from that particular node. Right. So, what we are saying here is, as you go to the first, we will color it as gray, that means a vertex has been discovered. We mark the discovery time, that is, we mark at what time we have reached this particular vertex. So, this is the time stamp that we have added to our standard DFS procedure. So, this time stamp tells us precisely the time or the first time a particular vertex is going to be visited. Once you do that, we just update the global time. Now, for every vertex in the adjacency list of view, if it has not been explored or been visited, that means the color is white, we move to that particular vertex and continue our DFS with that vertex as the current vertex. If this condition fails, that means if you visit a vertex and see that all its adjacent vertices are either gray, that means they have already been visited, that means you have no incident edge on U which has not been traversed. In that case, you have exhausted the adjacency list of the vertex, or there are no more adjacent vertices to be explored or to be visited. In that case, you color the node as black. A black field would indicate that all the vertices which are adjacent to these vertices have already been visited. Once you do that, you mark the time. So, for every vertex, you are going to time stamp it in at two points. One, the first time where it is going to be visited, that is the first time it will move from white to gray, and a time when it is going to become black. So, the DFS algorithm is going to be modified to add this time stamping features. That is done by coloring the nodes as you visit them and as you finish with working with a particular node. Gray would mean a particular node has been visited, but the adjacency list of the node has not been exhausted, whereas a black color would mean the adjacency list of the vertex has been exhausted. That means, from there probably you have to backtrack, that is, you cannot go further in the search from a black node. So, let us look at an example where we do the time stamping. So, initially all the vertices are going to be colored white and are going to be initialized to 0. So, we have not shown this in the figure, but initially all vertices are white and time stamped initially to 0. Now, as we visit a first, we update the time stamp there and make it gray. After that, we try to investigate or search the adjacency list of this vertex. We see that there are two white vertices. So, we pick up one randomly and move our search or to the next vertex, which is V, and make it gray and timestamp it as 2. So, as we have moved from here to here, V has been marked gray and the timestamp is updated. Then we look at the adjacency list of this. We find a white vertex, move there, mark it as 3. Now, as we move here 3, we move back, we look at the adjacency list here and move to this particular node and see that this is not visited. So, mark it as 4. Now, as we go from here to here, we see that all the vertices which are adjacent to this are already visited. So, we color it black and update the final time or the so this is visited at the 4th step and marked as black at the end of at the 5th step, that is at 4th we reach it, and then we check the adjacency list. We see that all the nodes are already visited. So, we color it black and also map a edge like this as a back edge. For working in topological sort, marking of the edges is not going to be crucial. It is the timestamp of the nodes which is going to be crucial. So, and then you continue your procedure. Now, we see that this is there is nothing to explore from here. So, we backtrack to a place from where this particular node was reached. So, we backtrack here. So, from here your search backtracks to here and you observe now that from this also there are no more nodes to be explored. So, we mark it as black and update the final stamp and go back again there is nothing more to explore. So, we keep on going back and we reach finally at this stage where all the nodes in this particular part of the graph have been visited and we also exhausted all the nodes in this particular graph. You see that after doing this, we still have not exhausted or traversed all the other nodes in the graph. So, we restart our DFS from this vertex and mark it with 9 and continue. So, finally, when we finish, we would have time stamp every vertex twice, one initially and one finally. Initially is for the first time that you visit, finally is when you have exhausted the adjacency list of that vertex. So, the DFS algorithm is going to initialize all vertices with white, visit each and every white vertex using DFS visit. A vertex is white if it is undiscovered, you will mark it as gray if it has been discovered, but not all of its edges have been discovered. Vertex is going to be black after all of its adjacent vertices have been discovered or the adjacency list has been exhausted completely. The DFS returns for every vertex u a time, that is discovery time du and a finish time fu. So, every vertex is going to be assigned two values, a discovery time and a finishing time. So, this is the standard DFS algorithm with this additional feature of time stamping. Now, this particular time stamping is going to be useful in understanding the order in which the tasks have to be accompanied or in which the vertices are going to be arranged. So, let us look at a directed acyclic graph. A topological sort of a directed acyclic graph is a linear ordering of all its vertices such that for any edge u appear before v in the ordering. The algorithm that we are going to look at is going to be based on DFS with time stamping. So, we are going to call DFS on the graph on which we want to do a sorting, and we are going to compute finishing times for each vertex v. As each vertex is finished, we insert it onto the front of a linked list. So, as you keep on darkening a vertex, you insert that vertex into a list. As you finish traversing all the nodes, that means as you finish blackening all the nodes, you keep on inserting it into a list. At the end of the DFS procedure, you would have inserted all the nodes of the graph in the linked list. The topological sort procedure will return the linked list. Let us look at this example. We have a graph which represents the way a person gets prepared in the morning, or after his bath, the way he gets prepared to leave to office. Now, we see that here this is an independent thing, does not depend upon any other, it does not have any prerequisites. So, it could be done at any time in the procedure. So, each of the vertex here is marked with its finish time and the discovery time. If this is the graph given G, we will do DFS of G. As you do DFS of G, it will return the discovery times and the finishing times, which are represented here. The first component is the discovery time, the second component is the finishing time. Now, once you finish this DFS, you look at a linked list in which you are going to insert nodes at the beginning based on the finishing times. So, first we are going to, so if you go back to the algorithm, as each vertex is finished, we are going to insert it into the front of a linked list. So, the first vertex that is going to be, that will finish the is going to be this particular, this has the least finishing time. So, as you do your DFS, this vertex is going to get exhausted or is going to be marked black initially. So, its finishing time will be least. So, that is going to be first inserted. So, this is first inserted into the linked list. After that, this node has the next finishing time. So, this will be inserted at the beginning of the linked list. So, initially your linked list will have only this node, then you are going to insert this and so forth. The next node that will be inserted will be having the next highest finishing time, which is here. So, this will be arranged here and so forth. The vertex which is going to be inserted last is the one which will have the maximum finish point, or which is going to be marked black at the end of the procedure, which is here. So, this is going to be at the, is going to be inserted last into the linked list. So, given any directed acyclic graph, if you do a DFS with time stamping, one can do a topological sort on this directed acyclic graph. So, you perform a DFS with time stamping and simply keep on inserting them in a linked list at the head as they keep on getting black in your DFS procedure. We look at one more application which is called biconnected components. Before we look at the application that we are going to work with, we are going to define a few things. A separation edge is an edge whose removal is going to disconnect a graph, and separation vertex is something which, if removed, will make the graph G disconnected. So, this concepts of separation edges and vertices are very crucial in understanding networks. So, if you look at networks, it is a critical point to the operation of the network. A separation vertex becomes very critical, because if the separation vertex is going to fail, your network is going to fail. So, separation edge and separation vertex are very key ideas in the study of networks. For example, if you have a network which is shown below, this vertex is a separation vertex, whereas this edge is going to be a separation edge. Again, you can have more than one separation edge or separation vertex. You see that even this is a separation vertex. So, this particular graph has 3 separation vertices. So, idea of separation edges and separation vertices are very key in having or in studying networks. So, we say a graph is biconnected if it has no separation edges and no separation vertices, or equivalently we say that any 2 vertices, there are 2 disjoint simple paths between u and v. That means, if you have any 2 vertices on a graph, it has at least more than one path connecting these 2 vertices, which means if one path fails, you still have another path to route your data. Such graphs or such networks are also called fault tolerant networks. That means, you can reroute the data if one particular path fails for some reason. Or we say a graph is biconnected if for any 2 vertices u and v, there is a simple cycle which contains u and v. So, a biconnected graph can be defined either in 3 ways. So, either via separation edges or in vertices, or using the fact that you have at least multiple paths between 2 vertices, or through cycles. So, G is an example of a graph which is a biconnected graph. We can easily observe that this graph does not have a separation edge or a separation vertices. So, one can actually check all the 3 definitions on this graph and verify that it is a biconnected graph. We also define what are called biconnected components. So, a maximal biconnected component is a subgraph consisting of separation edge of G and its n vertices. An edge belonging to exactly one biconnected component. Example of a graph with 4 biconnected components. So, we see that there are 4 biconnected components. These are basically the interactions. We also have a non-separation vertex which belongs to exactly one biconnected component, and we also have a separation vertex which belongs to 2 or more biconnected components. So, that is an example which is here. So, biconnected components of a graph G is a maximal biconnected subgraph. To find biconnected components, we are again going to use the graph traversal technique, depth first search. Before doing that, we look at a few more concepts. Given any relation on a set S, we define an equivalence relation which satisfies the 3 properties of reflexivity, symmetric and transitive. We say an relation is reflexive if and only if every point in the set is related to itself. Similarly, we say a relation is symmetric if x and y are related, then y is and x are also related. And similarly, we define transitivity, which says that if x and y belong to R, that is if x and y are related and y and z are related, then x and z are related. So, equivalence relation is a very important idea, and there are many relations which are equivalence relations, which are which represent some natural property of a problem. A key result is, if you have an equivalence relation, then that induces a partition of S into equivalence classes. This partition is going to be important in determining the biconnected components. So, if you have a equivalence relation, then it induces a partition on the set S. In terms of graph, suppose we define a relation which says that vertices are related if there exists a path from V to W. Then it is easy to prove that it is an equivalence relation. When we define a path from V to W, trivially we understand that we always have a path of length 0 from the vertex to itself. That is, you always have a path from V to V whose length is going to be 0. It is easy to check that such a relation is an equivalence relation. And crucially, if you look at the partition which is induced by this equivalence relation, precisely gives us the connected components of the graph. What we are going to look at are the biconnected components of the graph. For that, we define a relation, and via this relation we are going to compute the biconnected components of a graph G. So, we say that two vertices are related, two edges are related. The relation is going to be called a linking relation. So, we say that E and F are linked if either E is equal to F or there is a simple cycle containing both E and F. So, in this case, if you look at this is a simple cycle which has D, E, F. So, we will say D and E are linked, E and F are linked, and so forth. So, we see that we can write down this relation and check it as an equivalence relation. The equivalence classes that it is going to generate are going to be A. So, the equivalence class of A is just going to have A, because along with A you cannot have any other, you do not have any other edge which is going to lead us to a cycle. So, A is going to be isolated or is going to be an equivalence class with only one single element A. Similarly, all these vertices or all these edges here are going to be part of one equivalence class. We see that B, C, D is a simple cycle, B, C, F, E is also single cycle. Similarly, D, E, F is also. So, all this are going to be related to each other. So, we can see that B is related to C, or D is related to E, or F is related to. So, we can see that all the vertices in this are all the edges in this particular class are related to each other. For example, if you look at B and E, then you have B, this is the simple cycle which has B and E as edges. So, B and E are related. So, easily we can check that this is a equivalence class of G defined by the link relation, and the final equivalence class is this. Now, we see that if I take the union of all these three partitions or of these equivalence classes, this gives us the vertex set V of the graph G, right. That means, the linking relation is an equivalence relation. So, it partitions V into equivalence classes, which are precisely given via the linking relation. We are going to use this fact to achieve the biconnected components. So, one can easily prove the following results. We already said the equivalence classes. What one can prove also is that a separation edge is a single element equivalence class of a linked edge. So, if you look at the earlier thing, so if you remove this particular edge, you see that you are going to have a disconnected graph. So, a separation edge is a single element equivalence class of linked edges. So, A is a separation edge, we know A is a separation edge. So, in a equivalence class, that is going to be a single element. Intuitively clear that this result is going to be true, that is a separation edge will have no other element in its equivalence class, and a separation vertex has incident edges in at least two distinct equivalence classes of linked edge. To finally get the biconnected components, we use another idea of what is called an auxiliary graph. So, in an auxiliary graph, we first do the DFS traversal, the standard DFS travel, and then form a graph using the DFS traversal. So, for every back edge that we have in the graph, we look at edges EF1, EF2, EFK, where F1, F2, Fk are the discovery edges that form a simple cycle with E. So, we form such a graph, which is called an auxiliary graph. So, let us look at, so our auxiliary graph will have all vertices. So, its vertices are going to be the labels in are going to be the edges that you have in DFS. So, G is a vertex, similarly H is going to be somewhere here, whatever. D is this is C, so C is here. So, your edges, the vertices of B, correct, are going to be the edges of G. Now, for each back edge you are going to have, so for each back edge, so you look at all the back edges of your graph. So, in this case the back edges are here, correct. So, the back edges are, let us mark them, E is a back edge, F is a back edge, J, let us not worry about J, and C. So, E, F, C are back edges. Now, for every back edge you look at F1, F1, F2, Fk, such that when you do that they form a simple cycle with E. So, now E, see that if I have this particular thing, then this is a simple cycle. So, E will be connected to G and B. So, if you look at, so E is going to be connected to G and B, and one can then form this auxiliary graph. For example, if you look at C, C is going to be related to B and D, because C, B, D forms a simple cycle. So, C is going to be connected to B and D. So, using this DFS traversal and marking the edges as back edge or a forward edge, we can create another graph which is called the auxiliary graph using edges as the vertices and using the DFS traversal as the for marking the edges in the auxiliary graph. In the worst case, the number of edges of the auxiliary graph is going to be proportional to Nm. So, if you look at your precisely auxiliary graph and if you look at the connected components of that, you see that each of this is going to be a biconnected component. Now, we see that This is a bi-connected component. There are no separation vertices or separation edges. So, its connected components will correspond to the link components of G, which in turn are going to give us the bi-connected components of the graph G. So, we have seen how depth first search can be used to do a topological sorting or identifying the bi-connected components. Correct? The bi-connected components are very crucial in understanding the efficiency of a network. They tell how fault tolerant the network is going to be. So, we looked at two important applications of DFS, namely a topological sort, which gives us how we can rearrange or how easily we can interpret the prerequisites structure of a graph. Whereas, in bi-connected components, typically network help us to understand how fault tolerant the network is going to be. Thank you.